I have the multiple choice graded on your tests. And I am not quite obviously done grading everything else. So I should have your grades posted this afternoon. Something that I do is I will allow you to make test corrections. So once you get these back, I'll kind of explain this in more detail, but the basic idea is you give me what the correct answer is and an explanation for the correct answer, and you can get half your points back that way. So if you're concerned about your grade, you can do that. If you're happy with whatever grade you have, then, you know, it's not necessary. I won't look at you sideways if you don't do it or whatever. It's less work for me if you don't do it. But if you want to improve your grade, that's a way that you can do that. So you will get those back on Monday or Tuesday, depending on which day you're in class. And then on the day of the exam, you bring the corrections back to. We are going to do most of chapter 7 today, which is on oxidation. I'm going to be skipping several parts of it. So mostly what we're going to be focusing on is what's the definition of oxidation, and then that last part on antioxidants, because you hear about antioxidants in foods all the time. So I wanted to make sure to cover that. And then we're going to be looking at lipids, which is the next chapter. And I will again have a video for you to watch on the day that you're not in class next week. So kind of heads up for that. I haven't decided which one I'm going to use yet, so I'll have to look into it. Any logistical questions or other questions before we get started? All right, I did have one person ask about the final exam. That is March 22nd, which is the Monday. And I don't know off the top of my head what time it is. I think it's one of the morning time slots, but I'm not positive. But kind of be preparing for the Monday. So we're talking about oxidation in foods. And so oxidation is part of the browning processes that we look at. And so whenever you brown meat, like you see this one is here, that's oxidation. So oxidation can be something that makes foods more flavorful. It can also, it changes the molecules that are there. By cooking things, of course, we are killing off some germs, so that can be helpful. But at the same time, it can also lead to some things like the rancidity, or it can be an indication that we do have germs present. So it's not good or bad. It's, you know, it's just a process. So let's look at what we mean by oxidation. So technically, oxidation means losing electrons. So we know that all elements on the periodic table can have a form where they have the same number of protons and electrons. And so if they have the same number of protons and electrons, they're neutral. But we mostly don't find our far left elements, the metals, as being neutral. Usually they're positively charged. So like this is a sodium ion. And in group 1, it commonly forms the +1 charge. And that's because these electrons sit in rings. And the first ring has 2, the second ring has 8, that's a total of 10. And so there's only 1 electron in that outside ring. So it's kind of like sticking your hand outside a window in a driving car, and you panic, your mom's just like, you're going to lose your hand. You know, somebody's going to drive by and it's going to come off. So that's what happens to the sodium. It's sticking its hand out the window as it's driving, and somebody, you know, drives by too fast and takes it off. Okay, so that's oxidation, taking away an electron, and it makes the charge positive. Now, anytime that happens, that electron has to go somewhere, and wherever it goes, it's taking its negative charge with it, and so the other thing is reduced. And we're not going to talk a lot about reduction, but those two things go hand in hand. So a lot of times you will hear about oxidation and reduction together.
I have class that.
So we determine the oxidation number of an element based on how many electrons it originally had and how many electrons it has now. So you just subtract the two numbers, and whatever's left over, that's your oxidation number. So if it's neutral, like oxygen in the air or nitrogen in the air, a diamond, all of these have an oxidation number of 0 because there's no charge on it. So we can kind of think of the charge and the oxidation number as sort of being the same thing. Okay, so if I have a charge on something, then I'm going to have the oxidation number be the same thing as the charge. So sodium has a plus, so it's a +1. Chlorine has a minus, so it's a -1. Aluminum in this case has a 3+. Now, if I just have a sheet of aluminum metal, that's going to be 0. But in this case, there's a charge on it.
You did.
And so there's a 3+ present.
And when we got back,
Try this out.
it's a
What is the oxidation number of each of these atoms or ions? And I wrote this question after,
mixture.
or without looking at the slides properly. So you might recognize some of these.
Oh yeah, no, I'm completely broke.
Okay, so hopefully we're getting the idea here that the charge just corresponds to whatever the oxidation number is. All right, in compounds, like if I had carbon dioxide or if I had water, they also have different oxidation numbers, and there's a whole bunch of rules that you can use to figure out what they are. They're not going to be real helpful for us for what we're doing, so I'm just going to kind of skip over that whole section that's on finding the oxidation numbers in compounds. So you're not going to have to do it for a compound, but you should recognize that the charge is the same thing as the oxidation number. All right, so food molecules. What we're concerned with is what happens when we oxidize our food molecules. And they're mostly made of carbon, oxygen, and hydrogen, primarily carbon and hydrogen. And so when we talk about oxidation, this generally is going to happen by adding oxygen to the molecule or by taking away hydrogen. Those are two ways that we can either add or remove electrons. So for example, if I take methane, CH4, which is natural gas, it has 4 hydrogens and no oxygens, and I burn it in oxygen, now the carbon has 2 oxygens and no hydrogen. So I've added oxygen, I've taken away hydrogen. So in that process, I have oxidized the methane. So that's kind of an extreme example where we take away all the hydrogens and add as many oxygens as we can. But we can do little things like that with our fats and our proteins and our sugar molecules simply by adding or taking away hydrogens and oxygens. So what happens when we do this? They tend to break into smaller pieces. And so your fatty acids will tend to break off in chunks of 2 carbons, and then it becomes part of this whole acetyl-CoA enzyme mechanism thing that is for biochemists. I'm cutting off the screen here. Let me do this. For sugar molecules, we've talked about this with caramelization. That caramelization process is oxidation. It's breaking it into like the buttery diacetyl molecule and some of the nutty flavors like the furans and things like that. So it just gets broken into smaller molecules. Now, if I burn sugar completely, which is what your cells are going to do, they're going to break it apart completely. I'm going to turn it into carbon dioxide. So here I have, this is the glucose, right? C6H12O6. The carbon has the same number of oxygens. So there's 6 carbons, there's 6 oxygens. And here I have twice as many oxygens as I have carbons. So I've doubled the number of oxygens. So that's adding oxygen. That tells me it was oxidized. In contrast, I had 12 hydrogens for 6 carbons, so twice as many hydrogens, and now I have none. So I have both taken away hydrogens and added oxygens. All right, so we've talked about this a little bit, but I just kind of wanted to remind you of some of this stuff that we've said before. Our fatty acids are the things that get attached to the glycerol. And they're attached through ester bonds, but until they're attached, we have the acid here at the end, the carbon, oxygen, oxygen, hydrogen. So this is what makes it an acid. This is the fatty part. And when we have no double bonds, we call this saturated. So this is a saturated fatty acid. And what that means is that there's many hydrogens on there as they could possibly be. So I can't add any more hydrogens, but I can take them away. And taking away the hydrogens is oxidizing it. And so these, remember, are the ones that are going to be more prominent in our fats, our solids like butter, lard, the palm oil and coconut oil, which are closer to solids at room temperature. We're going to have a lot of these saturated fats in them. They pack very tightly, and they tend to be more involved in clogging arteries. So doctors kind of say, you know, let's avoid those saturated fats if we can. All right. So if we have saturated, we also have unsaturated. So that just means there's double bonds. And the double bonds have to be between two carbons. This is poly because there's more than one. If I only had one, it would be mono. This is trans. Okay. When it is flat on top, it's cis. All right. So trans, we get kind of a zigzag. Cis, you get a flatness. And you can start to cover the height. So the shape of the cis is kind of a trapezoid here. And the shape of the trans is still that kind of zigzag pattern. So our key points here is that fats can be oxidized, but the unsaturated, the ones with the double bonds, are more easily oxidized than the ones with no double bond. So the double bond is more reactive. And when they are oxidized, they start to smell rancid. In cooking, they're going to produce also some really good flavors as well. But if it's just oxidized in the air, it tends to smell rancid. All right, so which kind of fat did I say was most easily oxidized? Okay, so we got things ranging from unsaturated to saturated to trans to polyunsaturated. So yeah, anything that's unsaturated is going to be more easily oxidized. So polyunsaturated would definitely fit in that category. And if that were like a free response on a test, I would definitely accept that. It turns out that cis fats are more easily oxidized than trans. That shape difference means that the trans looks more like a fatty acid, and it's more difficult for the oxidation reaction to happen at that location. So it turns out that trans is kind of in between cis and saturated. All right, so we talked about some of the different ways that oxidation can happen. So if I tell you that a meat has been oxidized, does that necessarily mean it has bacterial growth on it? All right, so it actually does not, because remember, cooking also is an oxidation process. So cooking can produce this oxidation. And even if we find the meat in the refrigerator has started to turn brown a little bit, what that only means is that oxygen has gotten there, but oxygen means that we could be feeding bacteria, which is why when things start to smell rancid, you might want to say, I'm not going to take my chances. We don't have a real quick and easy test to say, is there bacteria there? We just know it smells bad. So that might be a case where you say, I'm not going to risk it. There's probably bacteria there, so I'm going to get rid of it. All right, so now we're going to start talking about antioxidants. And in order to understand the way antioxidants work, we kind of need to understand that electrons like to run around in pairs. So bonds between two atoms are made up of 2 electrons. So if I have a double bond, then it's 4 electrons. And sometimes electrons aren't in bonds. They are what we call lone pairs, but again, they're paired up. So we're kind of moving away from the idea of a lone pair because that's sort of an oxymoron to be both alone and a pair. But non-bonding pairs is another way that we talk about. So either way, electrons want to be paired up. And so if we ever have an electron in a situation where it is not paired up with something, that molecule becomes very reactive. So we call these molecules free radicals, and sometimes you'll hear on commercials for things that have antioxidants that, oh, it's going to neutralize these free radicals. So mostly free radicals don't happen a whole lot in nature. There are a couple of pollutants that are free radicals. So nitrogen and oxygen will combine in a couple of different ways to form odd numbered electrons. So nitrogen monoxide is 5 outside electrons, valence electrons from the nitrogen, and 6 from the oxygen. So you have 11 total. So that's a free radical. And that happens when we have nitrogen and oxygen in the air that react with one another. And usually that happens when there's either high heat or electrical sparks. So it could come from lightning, but it could also come from things like motor vehicles or power plants, things like that. So in places where you have a lot of that industrial stuff going on, you end up having more of this nitrogen monoxide. And there's another one, nitrogen dioxide, which is also a free radical. So what does this mean that it is more reactive? It's going to interact with whatever molecules it comes into contact with, and that might be your cells on your skin, your mucous membranes, so like your tear ducts, the insides of your nose and mouth, all of those tend to be pretty susceptible to attack by these kinds of things. And then once it gets into your lungs and things like that, and inside the cells, it can start interacting with the DNA. And so it can kind of break apart the DNA, put little kinks in it where there aren't supposed to be kinks, and all of those things can lead to either killing the cell or it can lead to cancer. Oops, I thought I had that on the line. Okay, so problems with free radicals is that they damage us and cause health problems. So an antioxidant is something that is going to stop a free radical. Why? Because a free radical wants an electron, and when you take an electron away from another molecule, that's oxidizing the molecule. So free radicals are really good at oxidizing because they want just one electron to take away and damage the other molecule. So an antioxidant is going to kind of get in the way. It's going to be kind of the bodyguard that's going to stand there and say, take me, not this cell. don't hurt the DNA, take me first. And so it generally is going to have a lot of outer electrons. And then I'm going to show you another feature of it that, that also makes it so that it's a little bit better for the antioxidant to lose the electron. But the antioxidant electron fills in the gap for the free radical. So we have that all paired up. The free radical is happy, and then we don't have as much damage going on. All right, so the way that this happens are that antioxidants tend to have what are called conjugated double bonds. So the double bonds obviously mean that we have these pairs of lines here. Conjugated means they're not all straight in a row. It means that we alternate, double, single, double, single, double, single. And what happens when we do this is that the orbitals or the places where those electrons exist in the double bond kind of lines up in a row, and they can spread out, okay? And we're not going to go into detail about the orbitals and all of this thing. What we need to know is that that conjugated double bond will allow all of the electrons to kind of spread out. And then it's like harder to tell that you're missing an electron, because instead of, oh, there's an obvious gap at this one location, everybody just kind of evenly spreads out. And it's like, okay, where is that gap? We're not really missing one. Maybe we're missing one. I don't know. And so even though technically the antioxidant is then going to be a free radical itself, that free radical isn't as reactive because we've spread out those electrons and made it less obvious that it's missing the electrons. Now, of course, our atoms and molecules don't have personalities and don't have minds that they can notice this. So what this really means is that it is more stable. It is a lower energy molecule than a free radical that is missing an electron but doesn't have this conjugated double bonds. So what we're going to be looking for, I'm going to show you the molecular structures of several of these antioxidants. What we're going to be looking for is particularly this. Remember, this is our aromatic ring that we saw in some of our fragrant molecules, but also some of them will have double, single, double going on as well. Okay. Okay, so the first one we're going to look at is sodium benzoate. And some of you may remember this one from the movie on the Poison Squad. This was one of the chemicals that they were testing out. Now, they tested at very high levels, and very high levels definitely are bad for you. It is used in lower levels. So as an antioxidant, it can protect us a little bit from free radicals that might exist. And it also can protect against germs and things like that. So it's most commonly found in places like sodas, jams, and juices. And this is because it works best in a lower pH. So a lower pH means we've got some H+ ions going on, and it's acidic, okay? Now, when they started regulating things that were going into food. So remember, it was in the early 1900s that they first said, hey, we can regulate some stuff. And they started off with alcohol. But it took them until the 50s to start being a little bit more specific about things. And that's because there's just so much that goes into our foods. But when you go to the grocery store, you probably think, when I pick up this box off the shelf, what's in it is what says it's in it. Like, they're not going to lie to me about what's in there, and what's in it should be safe to eat. And those are things that we kind of take for granted now. And that wasn't something you could take for granted 100, 150 years ago. So one of the things that they found was that people were selling honey that was mostly corn syrup. Okay, but at the time, there was no law against that. You could say this is honey and put corn syrup in there, because there was nothing that said you have to label it with what it actually is. And so the reason we have ingredients lists now is so that, or is because of the regulation that you have to tell people what is in this. And then the other part of that regulation is it has to be safe. And that's where that poison squad really kind of came in and said, hey, you know, we need to be paying attention to all of these things that, you know, the food companies are saying, yeah, it hasn't killed anybody yet, which doesn't necessarily mean that it hasn't hurt anybody. And really, were they paying attention to whether or not it killed anybody? Getting back to sodium benzoate. In small amounts, this is deemed to be perfectly safe. And in the 1950s, rather than going through and doing tests on every single little chemical, what they did is they went to doctors and they said, you know, look at this list of chemicals that might be in food. Which are ones that you would say, please don't let people have this. This is hurting people. And so the ones that they said, no, that seems to be okay. They called it generally regarded as safe. So sometimes you'll see this phrase GRAS, generally regarded as safe. And so what that means is that at the time when this law came into effect in the 1950s, there hadn't been a lot of studies on it, but there wasn't a lot of evidence that it was hurting people. Now, since then, of course, things that we were not sure about, there have been studies on, and some of them have been taken off of that generally regarded as safe list because no, we think it actually might be harmful after all. And then there have been some things that they've tested and they said, okay, now we actually have the evidence that this is safe as well. Okay, so sodium benzoate, what might be problematic about it? So this is an artificial antioxidant. This ring by itself, the aromatic ring, is called benzene, and benzene is a carcinogen. And if you heat this up, you can turn it into benzene. And if it reacts with citric acid or ascorbic acid, things with vitamin C in it, that also can turn it into benzene. Okay, so most sodas, like your soda cold, doesn't normally have citrus in it. Probably not a good thing to have with your Fresca or your, you know, your lemon lime sodas or whatever. But one thing that's kind of problematic in my mind is that sometimes on the internet, you'll see, oh, here's this great recipe. All you do is add a can of Diet Coke or add a can of Dr. Pepper. And while that might taste good, there's a good chance that you might be producing some benzene. Now, if you have that once every couple of years, it's probably so low that it doesn't matter. You know, it's kind of like with, you know, that ginormous sundae that you really love, but you know is bad for you. If you do it once in a while, not too much of a problem, but it's probably not a good idea to make a habit of cooking with sodas because they are going to have this, which when heated turns into benzene, which is a carcinogen. If that makes sense. Okay. I guess I should have popped that up before. So vitamin C, which is ascorbic acid, plus sodium benzoate is going to give us benzene. Heat gives us benzene, and benzene is a carcinogen. Okay, so the next one is the only one that we're really going to talk about that doesn't really have these conjugated double bonds, but sulfur dioxide is also an antioxidant, and it is used for a couple of different reasons. So antioxidants help preserve foods, and so it's commonly used with dried fruits. Sometimes it's used in sodas. Sometimes it's used in wines as well. It is also what's called an antifungal, which means it keeps things like mold and fungus from growing on things. So it's commonly used in dried fruits where there's just small amounts of moisture. The other thing that it's going to do is it's going to preserve the brightness and color, because colorful compounds often come from these conjugated double bonds as well. And so if we can protect those conjugated double bonds, then we can protect the colors. And so it's much more appetizing to have your dried cranberries if they're, you know, this really bright red color than if they're, you know, kind of a dull brownish color. And so that's one of the reasons why it's used in for dried fruits. Most people, not real problematic. However, people who are asthmatic tend to be sensitive to it, where it can cause some health problems with that or some allergic type reactions with that. So if you're somebody who has asthma and you found, gosh, I can't really have trail mix, or I can't really have, raisins or dried fruit, this might be why. It might be the sulfur dioxide. To connect back to chapter 4, this is an acid anhydride. So we said metal oxides, when mixed with waters, form bases. This is a non-metal. Sulfur is a non-metal. Non-metal oxides mixed with water are going to form acids. And we can tell this is an acid because we got that hydrogen out front. Okay. All right, so another artificial antioxidant we'll see is BHT, butylated hydroxytoluene. Don't need to know the name, but if you see BHT on a label, this is what it is, and you'll notice we've got that conjugated double bond in there. Some countries are fine with BHT, other countries are kind of on the, I don't know if that's safe. And so there's been a move away from BHT to something called BHA, butylated hydroxyanisole. So this bottom picture is BHA, and notice it has the OH on there, the alcohol, which is why the name anisole ends in OH, OL rather. So this is found all over the place. It's in just about any kind of food you can imagine. It's also found to preserve cosmetics. So we don't want to get bacteria or fungus in makeup and have that potentially cause reactions with the skin or the eyes. And it's also used to preserve things like rubber and petroleum, because we want to keep those things from being oxidized. When rubber gets oxidized, then it breaks apart rather than maintaining its elasticity. So we don't want the rubber tires on cars to start to fall apart. So it protects those. So it focuses on preventing oxidation, mostly of oils and fats. It can prevent oxidation elsewhere, but mostly oils and fats. And it does help to preserve both the flavor and the odor. So remember that the odor of something doesn't necessarily mean it's gone bad. And so a company selling food that knows, hey, it's going to be safe to eat for a long time, but maybe just as it starts to oxidize, it's going to smell a little bit off. We want to keep it from smelling off so people will keep buying. So if you imagine like potato chips or something like that, they know they put it in the bag, it was all sterile, they put it in the bag, there's no bacteria in there, but because there's a lot of air in that bag, then those oils maybe would start to oxidize. Well, they don't want that to smell bad, and so they might put a little bit of this in there to keep it smelling nice and fresh. And so, and then the last line here, this is the BHA. So you can see they're very similar molecules, not exactly the same. Okay, we are back. So we just talked about 3 artificial antioxidants. And so when people talk about foods having artificial preservatives, those are the kinds of things that they're talking about. But there are a lot of natural preservatives. If the natural preservatives exists in the food naturally, then it is considered natural. If that natural preservative is added extra, it is considered artificial. So if I have vitamin C in my orange juice, that's considered natural. But if I take vitamin C and add it to something else in order to make that thing more preserved, even though vitamin C is natural, it's considered artificial to that particular food. So that's kind of one of the distinctions between natural and artificial. So vitamin C doesn't have a benzene ring, but if you look over here by the oxygen here, we do have a double bond, a single bond, and a double bond. So we've got a little bit of that conjugation going on. It is named ascorbic acid because scorb refers to scurvy and A means not. So it's basically the anti-scurvy thing. And we will, I think tomorrow we'll talk about vitamins. When we start talking about vitamins, we'll go a little bit into more detail about where this whole idea with vitamins, vitamin C and scurvy came from. That's kind of an interesting backstory. But this was one of the very first vitamins that was discovered, along with some of the B vitamins. And the idea of a vitamin is that our body doesn't produce it naturally, but we need it to live. So ascorbic acid kind of fits into that category. Oddly enough, pretty much every other living thing, mammals and plants and things like that, make their own vitamin C. And so eating just fresh fruits and vegetables, you get plenty of vitamin C every day. But if you are going on a long trip somewhere, say it's the 1800s and you have to cross the ocean, and so you're going to be on a boat for 2 months, your fresh fruit is not going to stay fresh for 2 months. So you're not going to have a lot of fresh things that you can consume. Now, you can have things like meats, and raw meats are going to have some vitamin C in them. So that's something that you can do. But once you cook the foods, the heat is going to break it down and destroy it. And so then it becomes less useful. So putting vitamin C in something you're going to cook doesn't really help you. Okay, so it is natural, but it isn't natural in everything. So when we add it to a cooked thing afterwards, that's considered artificial, and it is necessary. So this is ascorbic acid. Oops. Give me a chance to jot these things down. And, you know, I've just got a picture of raspberries because it appears in raspberries, but like I said, it appears in pretty much any fruit. Tea leaves, lots of things have ascorbic acid. Okay, another one, this was really in the news a lot, maybe about 10 years ago, and you don't hear about as much now, but this is resveratrol, and it is found very commonly in the skins of grapes. And so grapes, grape juice, wines, particularly red wines, which use the red skin part in their coloring, they're going to contain this compound. And you can see we've got 2 of these aromatic rings, and we also have the conjugation in between. So really got a lot of conjugated double bonds going on there. And so this is an antioxidant that is found naturally in a lot of things. Some people have tried to market it as a supplement, like, hey, you know, take a pill full of resveratrol and that'll make you, you know, healthier. Doesn't necessarily work that way. There's kind of conflicting evidence. So usually with this one, it's best to have the natural food rather than trying to take a supplement. Come on, there we go. Okay, flavonoids. This is a whole group of compounds. So it's not just one particular compound. And they are found in darkly colored fruits. So like blueberries have a lot of flavonoids in them. And there's another group of compounds called flavanols that are also closely related. And it really just has to do with whether you have one particular thing having a ketone or an alcohol, and you know, we're not going to go into that. But things that have darker skins, blueberries, raspberries, plums, things like that, tend to have more of these flavonols in them. And so sometimes they'll say you should eat a rainbow of fruits and vegetables, and that's because you're going to get some of these antioxidants that are found naturally in these darker skinned things. Now, if you look at something like an apple, particularly if you don't eat the skins of the apples, those aren't going to have as many of those compounds. That's a lighter colored fruit. Good news again about chocolate. So we talked about chocolate had theobromine in it, which not good for dogs, might kill our dogs, but for us, it can lower blood pressure. It also has that phenylalanine, which kind of gives you that sense of euphoria and love. And it also has catechins. So catechins is another category of the antioxidant compounds. In chocolate, the catechin is in particular epicatechin. So it's got catechin in the second part of its name. And we can see again, we got these rings here with the conjugated double bonds. Okay, so chocolate actually does have a lot going for it if you ignore the fact that it's full of fat and sugar, which I am happy to do. Okay, so that kind of covers what we're going to talk about with oxidation. I know it feels like that's a lot of stuff. I'm probably not going to ask you, to give me details on specific molecules. I would like you to be able to distinguish between what is an artificial antioxidant versus the natural antioxidant. So you should know that when we talk about flavonoids or flavanols or catechins, that fits in the natural category. And when we talk about BHT, BHA, and sodium benzoate, that's in our artificial category. And you should probably also be aware for the 3 artificial ones, kind of where you would find them and what are some things you need to be cautious of. So with the sodium benzoate, we need to be cautious that it can produce benzene if we heat it or react it with vitamin C. And with the sulfur dioxide, people with asthma can have a sensitivity to it, similar to an allergic reaction. All right, so on Monday and Tuesday when you're here, we're going to take a look at some natural antioxidants. So in addition to vitamin C, vitamin E is also an antioxidant. And we are going to do an experiment where we can see, literally, visually, see the antioxidant action at work. So that's coming up on Monday and Tuesday. All right, so I'm finishing a lot earlier than I had intended to, but I don't want to cram more material in here and kind of overload.